In this lecture, we look at the calculation revolution. Now, I just want to note very briefly that this chapter on the calculation revolution only comes in the second edition of your textbook. The first edition doesn't actually have this chapter at all. I think this suggests two things. First is that it's introduced by popular demand, or maybe for completeness of the story. Once they realized that this section on computers was missing, perhaps they decided to incorporate it. And then second, that it allows us to be perhaps a little bit more critical than some of the other chapters. So we'll see what that looks like as I go through the material for this week. But I'll just say to keep an open mind as we're reading through the chapter or talking through the chapter. Okay, so what is the calculation revolution? Well, your book is going to draw this thread between the following four episodes in the evolution of calculation. We're going to start with the telegraph network. Now, it's noteworthy here that the telegraph network in your book comes after the invention of the analytical engine. I flipped this just because the telegraph itself comes before the analytical engine, and I think it makes the narrative a little bit more fluid. So we're going to start with the telegraph network, even though the network itself doesn't really get cemented until after the analytical engine. Okay, so we're going to go from the telegraph network to the analytical engine of William Babbage. We're then going to move to Bletchley Park and the code-breaking efforts there during World War II. And then we're going to end with the ENIAC, the first programmable computer. Now, let me just note here that we're stopping before we get to the internet or to the use of personal computers. There's a good reason for this. So the chapter is the calculation revolution. It's not so much the emergence of the field of science, computer science, but rather the changes in calculation that have changed society, so industrialized society. And so we might wonder then, what is it that's going to unite all of these projects? Because these seem like really diverse efforts. So the telegraph network and ENIAC, what do they really have in common? So here's where I think that it being a new chapter allows us some flexibility in interpretation. We might say there's conceptions of computation at play in all of these. But I think that might even be a hard argument to make. As we'll see going forward, the telegraph network doesn't really seem to be a computational device. The alternative image is that there's different conceptions of intelligence at play in each of these. And I think that we'll see this, or at least that's the argument I'll try to make in this lecture, is that we can thread this needle through these different episodes by looking at the conception of intelligence at play in society at the time, and then how these efforts have sort of changed the conception of intelligence. We'll look at different primary source quotations to see what conceptions of intelligence either the makers of these devices have or people commenting on these devices at the time have. Okay, so let's go into the instances or the different episodes, and then at the end of each episode, I'll bring this question of intelligence back up. Starting with the telegraph network. So before we talk about the telegraph network, let me briefly say a few things about telegraphs themselves. So here's an image of a telegraph. What were people saying about telegraphs? So here's a quotation from George Wilson, a chemist, in his book Electricity and the Electric Telegraph. As in 1852, he writes that the telegraph led to the practical reduction or annihilation of time. So let's think about why he might be saying this. Before the electric telegraph, there was just ways of optically signaling at distances, but they weren't very good. So you could say like, oh, I'll have one flashlight if no and two if yes, or something like that. But that can't travel very long distances, right? And then you have to agree with somebody what the interpretation of the optical signal is going to be beforehand. You're really limited to just very simple messages. The electric telegraph allows you to send really more complicated messages at vast distances. And it goes at the speed that electric signals take to transmit. If you saw the passing of time as measured by or constrained by the time it takes to pass a message to somebody, the way that you understand time really changes with the invention of the electric telegraph. That's what Wilson is trying to say. Okay, so another quotation, this time from Lord Salisbury, who's the UK Prime Minister, circa 1889. He writes, "The telegraph assembled all mankind upon one great plain, where they can see everything that is done, and hear everything that is said, and judge of every policy that is pursued at the very moment that those events take place." So two things to note here. So first is that he's really emphasizing this equality that the telegraph brings, so it assembles all of mankind into one plane. And this is to be contrasted with like a hierarchical understanding that probably preceded this time period, right, of only certain people could have access to the information, etc. And the other thing to note is that it's a very politically informed or politically situated kind of claim, because he's talking about people judging policies, and so you can see that the UK Prime Minister might be more likely to make that kind of claim. Okay, he continues. He writes, "The action of the telegraph, combined together almost at one moment, and acting at one moment upon agencies which govern mankind, the opinions of the whole of the intelligent world, with respect to everything that is passing at that time upon the face of the globe." So the idea here is that not only is it bringing everybody on the same playing field, but it's also combining together the opinions of everybody of the intelligent world who had access to a telegraph. Okay, so it's acting as a leveler, as a way of uniting humanity, and also maybe changing our conceptions of space and time. So now we move to the telegraph network. So the first transatlantic cable was laid in 1854, and it took 4 years to complete, but then it only functioned for 3 weeks. After 3 weeks, somebody passed a signal of too high voltage because it took forever to transmit, so they were trying to speed it up. So they passed a signal that had too much voltage, and then they fried the cable. But the first official telegram to transmit across this cable was a letter from Queen Victoria to President Buchanan of the US in 1858. And then in 1865, they laid a cable with much better material, and that served for a while to transmit signals back and forth. Then, of course, this becomes a global thing. So the telegraph network, once it's laid, is able to unite across the globe. So this is all during the Victorian era, and commentators are talking about the telegraph network in metaphors oftentimes, and what they're analogizing is the human central nervous system to a telegraph network. They're saying that the network of cables are like the nerves, and then the telegraphs themselves, the telegraph machines, are like the brain. So the nerves are transmitting to the brain, and then the brain is transmitting down along the cables or the nerves. This kind of metaphor really emphasizes the instantaneous nature of the transmission. And then another interesting feature about these metaphors were that the breakdown of the telegraph network was often analogized to hysteria or to insanity in people. And so if you were to make this analogy between the human nervous system and a telegraph network, the breakdown of the telegraph network and the breakdown of the human were seen as like when you didn't give them enough vigilance or attentiveness, each would break down. So the human breaks down into hysteria, whereas the telegraph network stops functioning. And so they both require vigilance and attentiveness in order to continue to operate. Now that's an interesting connection to how women were seen in this time period, because of course women were the ones who were going to experience hysteria and who therefore were seen as like not having enough vigilance. Okay, so if you want further evidence of this metaphor, here it is in Schoolhouse Rock.
There's a telegram for you, ma'am, and the message is clear. It says there's something bugging you and buzzing in your ear. The results can be quite itchy, so what is your reply? Tell your arm to swat that fly. a telegraph line. You got yours and I got mine. It's called the nervous system, and everybody understands those telegram commands, and you know that everybody better listen.
The central nervous system is the brain and the spine. The brain controls the system and the spine is the line. Telegrams come in to tell what's happening to you. Then telegrams go out to tell your body what to do.
Okay, so now we can consider what conception of intelligence do commentators in the Victorian time period have about the telegraph network. In other words, what is the background conception of intelligence at play when your book, for example, writes that, quote, the telegraph network was intelligent according to its promoters because it was just like the human brain and nervous system, end quote. What is the background notion of intelligence that allows them to say that the telegraph network was intelligent? Now, I'll just say a few things. So you might say, that's really crazy. How would something that just transmits information be intelligent? Actually, it would be the information being transmitted that would be the intelligence, and the telegraph network is just a way of transmitting that information. In other words, sure, the telegraph network unites across the globe, but the telegrams, the information sent, are the things that really have intelligence. That would be a way that you could disagree with the textbook. On the other hand, you might say, well, maybe that was the conception of intelligence at this time period, was just the ability to unite across vast distances instantaneously. So the idea here is something like the ability to communicate across these distances is a kind of intelligence in and of itself. You might be able to find similar kinds of claims actually when the internet is emerging, is the ability to unite and to quickly gather information creates a kind of intelligence or super intelligence, if you will, based on that information. Okay, so those are two ways that you can either agree with the book in saying that the telegraph network was intelligent, or disagree with the book and say, actually, it was just the ability, it was actually just the telegrams themselves that represented intelligence. Our next episode is the invention of the analytical engine by Charles Babbage. So Charles Babbage, sometimes known as the father of computing, goes to Turin, Italy, and there he talks to a group of Italian scientists in 1840, and he describes what will later be called the analytical engine. This is the only public explanation he ever gives of this machine, and so it's significant because of the interest that came afterwards. Luigi Menabrea, who's at this meeting, is an Italian mathematician and actually later becomes Prime Minister of Italy, and he in the audience for Babbage's talk and ends up publishing a book called The Sketch of the Analytical Engine invented by Mr. Charles Babbage. He publishes this in 1842. Ada Lovelace, who was born Ada Byron of Lord and Lady Byron, who you may have heard of, she is sometimes called the mother of computing, and she sees this book and wants to translate it. She actually ends up corresponding extensively with Babbage and publishes a translation of the book, but she ends up amending her own notes. The notes end up being 3 times longer than the original article, interestingly enough, and so people that study these two documents tend to say that people didn't really understand the significance of the analytical engine. Babbage wasn't that great to get along with or to correspond with, and so people really kind of avoided working with him or understanding the significance of what he'd invented. But Ada Lovelace's translation is thought to have really understood the significance and then demonstrated or shared the significance with the broader community. Now, the analytical engine was never actually constructed, but an artist has recently tried to imagine what it would look like. So here's an image of what the analytical engine would look like according to Sidney Padua if it had been constructed. On the left of the picture, we see Charles Babbage. On the right, we see Ada Lovelace. And in terms of the machine itself, on the very left is the steam engine, which powers the whole thing. Then we have the storage as this back section. It requires that entire back section for storage. We have this tower, that's the CPU in today's terms. And then Ada Lovelace is using punch cards to interact with the machine itself. Okay, so with that introduction, let's look at what Ada Lovelace says about the intelligence of this machine, or lack thereof. She writes, "The analytical engine has no pretensions whatever to originate anything. It can do whatever we know how to order it to perform. It can follow analysis, but it has no power of anticipating any analytical relations or truths." End quote. So what she's saying here is, I have punch cards and I tell the machine what to do. It has no power of anticipating relations or truths. That would be intelligence, but it can't do that. It can only do what we know how to order it to perform, she says. And so I think she has a very strong notion of intelligence in the background, one that requires a machine to anticipate analytical relations or truths. And so when we ask what conception of intelligence does Lovelace have, the answer is something like the ability to anticipate truths would be a form of intelligence. And because computers, or at least the analytical engine, couldn't do this, she did not see them as having intelligence. Okay, our next episode is that of Bletchley Park. Now, Bletchley Park was a gathering place for code breakers during World War II in England. There's been a lot of popular media coverage of Bletchley Park, so if you're interested in any of these themes, please feel free to watch these movies, read these books, watch these shows. Okay, so Bletchley Park, as I said, it was the center for Allied code breaking during World War II. At the peak of code breaking efforts, it employed nearly 10,000 personnel. Now, your book notes that this is the thing that was really innovative about Bletchley Park. It wasn't so much that there was, at least at the start, there wasn't like a unique methodology or a unique computer design or anything like that that really set it apart or made it successful. Eventually, we get there, but at the start, it's just the sheer number of people all organized in a way, in a hierarchical way that allowed for code breaking efforts to be really streamlined and really efficient. Now, it's also worth noting that it's thought that about 75% of the personnel were women, specifically of middle-class backgrounds, and they often had degrees in math, physics, engineering, etc. It's worth remembering that the men are at war in this time period, and so the barriers to women entering these kinds of professions were probably much lower, and so they were able to go into this these code-breaking efforts. Whether or not their contributions were later acknowledged, they were at least there doing the work. Okay, so the person often seen as the icon of Bletchley Park was Alan Turing. He worked, at least for some time, in Hut 8 of Bletchley Park. Here's an image of that. And he designs this computer known as the bomb. It's eventually going to crack the German Enigma cipher. But it's worth noting that he's not doing this on his own. So the bomb design undergoes significant refinement by Gordon Welshman in 1940. And then it's engineered, put together by Harold Keene's British tabulating machine company. So it was Turing, with the help of everybody else that was involved in the manufacturing of the bomb, that gets it off the ground. The National Museum of Computing, which now exists in Bletchley Park, actually rebuilt the bomb and now is on display. You can see the front on the left and the back of the machine here on this slide. One of the reasons I've introduced Alan Turing here is because we're going to read a selection from one of his articles published in 1950 called Computing Machinery and Intelligence for the end of module essay for this module. In this essay, Turing opens with the question, can machines think? And so we're really going to be addressing the question of the conception of intelligence Turing has in the background of this article in that end of module essay. So I'll save the answer for this question for you all to discuss in your essays, but just know that Turing's conception of intelligence will be really interesting to contrast to Ada Lovelace's. Okay, and no discussion of Turing is complete without discussing his eventual fate. So Turing gets prosecuted for homosexuality by the British government in 1952, and he ends up accepting chemical castration as an alternative to prison as his punishment. He dies in 1954 from cyanide poisoning. It's a little contentious whether it was suicide or not, so sometimes he would have chemicals that he'd experiment with in the room next to the room he was found in, but others think that it was likely suicide that led to his death in 1954. Okay, so our final episode for this chapter is the development of the first programmable computer in 1945 called the ENIAC. The ENIAC is seen as one giant calculator, so it was equivalent at the time to 2,400 humans worth of computing power. The cost was $500,000 at the time, which would be equivalent to about $6 million today. It had two designers, John Moshley and J. Presper Eckert, and it later inspires those two and John von Neumann to develop the successor of the ENIAC called the EDVAC. Interestingly enough, the ENIAC wasn't fully constructed, and these three were working on the EDVAC already. The innovation of the ENIAC was its general purpose programmability, as in it did not require somebody to go in and mechanically or physically change the computer in order to perform different tasks. You could program it to perform different tasks, which we take as a given today with our computers, but at the time that was a really big innovation. It also meant that you needed programmers to tell it what to do. And interestingly enough, there were 6 women programmers that were the main programmers of the ENIAC. Now, we often see pictures of these early computers, and they're gigantic, like entire buildings or entire rooms at best, which makes us wonder, or at least makes me wonder, what was going on? Why were all these computers so big? And the answer is just because they required these huge vacuum tubes. So the ENIAC had 18,000 vacuum tubes, and that was what allowed it to perform the calculations. As your book notes, these vacuum tubes were later replaced by transistors, and this invention of the electric transistor actually won a Nobel Prize, and the 3 men that were working on it were from Bell Labs, so they got the Nobel for the transistor. That's what allowed computers to start shrinking from entire buildings to get smaller and smaller. Okay, so the ENIAC was known by the press as this giant mechanical brain. Let's look at this article from the New York Times circa 1946 to see what the press was saying. So again, we see our 2 inventors, Moshley and Eckert, and the New York Times commentator says, quote, "Basically, it does nothing more than add, subtract, multiply, and divide." Very simple mechanical, or very simple, just a giant calculator. But, he continues, "The machine, however, can do much more. It has the human faculty of memory, 4 kinds of it, to perform certain tasks in the proper sequence." We see here that the New York Times writer has called this the human faculty of memory. So it's attributed this human intelligence to the computer in the form of memory. And the intelligence here is the ability to have memory. But let me just remind you that the innovation isn't that it has memory or storage full stop. Remember, even the analytical engine had ways of storing information. The innovation is that there's a stored program. The program, which removes the need to physically reconfigure the machine and tells the machine the tasks to perform. That's the main innovation, not that it can store numbers, etc. So we might ask, what is the conception of intelligence that the press has for the ENIAC? what does this New York Times article reveal about what intelligence was seen as when looking at the ENIAC? And it seems the answer to this is intelligence is the ability to change how we interact with something based on the input. So we get some kind of input, and then the way that we interact with it isn't set from the get-go like all other machines had been before the ENIAC, but rather we can program the ENIAC to interact in various ways with different kinds of inputs. Okay, so let's return to the main question of this lesson. What was the calculation revolution? Maybe we can claim that it was a steady progression of increasingly sophisticated computational devices. We saw that steady progression as we moved from the telegraph network to the analytical engine, to the code-breaking efforts in Bletchley Park, and then finally to the ENIAC, and later maybe to the personal computer and the internet. An alternative answer to this question, though, is that it's a steady progression of increasingly sophisticated conceptions of machine intelligence. So we started with a conception of machine intelligence that was an analogy to the human nervous system. We then moved to one that asks that machines be able to derive truths and do so independently of human input. Turing presents a distinct account of intelligence, which you'll read about in the end of module essay prompt. And then we see another one in the ENIAC discussion of the ability to, on the fly, interact with different kinds of information differently. So to be programmable to change how we interact with information. So these are different conceptions of intelligence applied to the machines through the years. And so maybe that's another way in which we can understand the calculation revolution, is the steady progression of different conceptions of machine intelligence.